okay.
So then like
Yeah. How long are we going
We have
today?
till whenever you want. They're here. Yeah, they're not going anywhere. Well, ideally till 4, but
Okay, well, sure. I think we'll be done by 4.
yeah.
Um,
But before that is fine too.
so
Or
the
after.
general kind of layout here is to talk about clustering in general, and then to specific packages that you might want to use for plotting, clustering and plotting. And please feel free to interrupt me if you have any questions. Okay. So, I mean, this is a typical clustering figure that shows up in papers. Often you will have each column will correspond to a sample, each row will be a particular gene, and you look at this thing and you kind of get a sense of what's going on, what patterns there are, what groups, and so forth. But this is a typical clustering. So we'll talk about clustering in general. So clustering kind of comes in 2 categories: supervised and unsupervised. In supervised, you're telling it how many clusters you think there are, and asking it to tell you what are the members of those clusters. So you might say, I think there are 4 clusters here. What are the members of the 4 clusters? Or what are the 4 clusters? And a very popular and good way to do that is called k-means. I'm not going to go into it, but just to say that there's an R function to do it. But we're going to use it here to make some points. So here are a bunch of points, which each one we can think of as a sample of some sort, or a specimen, if you will. But we have these I'll just call them samples for now. We have these samples here. Each one has an x value and a y value. And if you tell k-means, give me 4 clusters, 4 classes, this is what you get. You pass in the x and y values, and it says there are 4, and these are the ones, and that's what you would expect. So that's good. If you tell it there's 3 classes, it also does something very sensible. It says, oh, okay, well, here's 1 class, here's another, and here's a third. So that's reasonable. If you tell it that there are 5 classes, I'm not sure exactly how it made the decision, but it breaks this one up into 2 classes, and then each one of those is a class for a total of 5. So k-means does what you tell it to do. Okay. But now we're going to move over to unsupervised clustering, where you don't tell it anything about how many clusters there are. And we're going to talk about hierarchical clustering. And in a minute, I'll get to why hierarchical clustering, but it's related to the notion of the question of how many clusters are there here. From one point of view, there's obviously 3 clusters, this one, and this one. But from another point of view, maybe this is a cluster and that's a cluster, and maybe there's 1, 2, 3, 4, 5, 6, 7, 8, 9 clusters. And I guess what I've done here is actually I've told k-means there are 3, so it does the reasonable thing, and then I told it there were 9, and it does the reasonable thing. But that brings up the point, how many clusters are there in this picture? Are there 3 or 9? Either one is a reasonable answer. So the point of hierarchical clustering is to say that clusters can be in a hierarchy. So at the highest level, there are 3. But then at a lower level, those 3 split up into, further subclusters. So the notion of a hierarchy is here, that you can have the 3 big clusters, and then each one of these clusters has, say, 2 subclusters or 3 subclusters. So that's the structure. So the notion of hierarchy is that there can be many levels in a hierarchy, all with different clustering, and it's all valid. and you represent this hierarchy with a dendrogram. Right? In this case, it splits. And by the way, typically the height of the dendrogram represents how different is the stuff on the left from the stuff on the right. So that's why we have hierarchical clustering. Okay, so when you have some real data, say some samples by some genes of some sort, there are a lot of questions that you have to answer for yourself. And I'm going to just kind of read them off, explain a little quickly what they are, but then we'll go into detail into each one of these and what I would recommend. So for one question is, how many genes are we going to represent? How are we going to choose which genes we're going to put in here? By the way, as an example, this has 2,000 genes. There are about 22,000 genes. You cannot plot 22,000 genes. You won't see anything. It's too many. So typically and there's for other reasons that I'll get into in a minute, you may not want to use all the genes. So you're going to use a subset, but how many, how to choose is an issue. And then you want to normalize the data, maybe, before you do the clustering. Then when you do the clustering, what notion of similarity are you going to use? So to say that these three things all are in a cluster is to say they're very similar to each other. Well, what is the notion of similarity that you're using? That's called the metric, and there's many of them. And then there are various methods of hierarchical clustering. The only one that I've ever had any experience with is called agglomeration. And the notion of agglomeration is that you start off with everything's like a singleton cluster. Every single sample is a cluster. And then you start saying, oh, I'm going to take those two and put them together. And then I'm going to take some more and put them together. So you start building up that hierarchy from the bottom up until you get to the top and there's only one left now, right? So there are different methods of agglomerating, of putting things, choosing how to put things together. So I'll talk about all of these now. So which genes? Well, there's two ways that I can think of to choose genes. There are actually many ways, but two popular ones might be pick the genes that have the highest mean expression, or you might look for the gene that has the genes, let's say, that have the top 2,000 highest standard deviation. I tend to use standard deviation because that takes into account the level of expression. Usually, let's say a gene that's got a higher expression is also going to have a higher standard deviation, higher variability. And but if you have a highly expressed thing which has no variability, it's probably not very interesting. So that's why I prefer this to that. But I suppose you could use either one, typically. And why do you not want things that are very lowly expressed? Because if they're very lowly expressed, you're probably just getting noise, and they're not going to help you understand your data. Okay, how many? Well, back in the days of microarray gene expression studies, I would try various ones, various numbers of genes. What I found was that, so I would try, these different numbers. I found that the clustering changed as I went from 50 to 100 to, each time the clustering significantly changed until I got to about 1,000. And beyond 1,000, it stayed pretty steady. The clustering stayed steady until I got to maybe, 10,000, half the genes. And then it started kind of just washing out, and there was no real clustering anymore. So I said, all right, I'll use 2,000 from now on. That's what I've actually done. So, you can do a similar experiment, if you're concerned that your data may be different. Normalization. Okay. A very popular way to normalize data, or it used to be very popular, it's less so now, I think, but is median polishing. And so the notion of median polishing is you want to know what's different between rows or between columns, but you don't want to know anything that's common to a column or a row. You want to subtract out all that. So what you might do is you say, okay, from each row, I'm just going to subtract off its median. So now each row has a median of 0, and you can see the positive numbers and the negative numbers above or below the median. So that's nice. And then you can do the same thing for the columns. Subtract off the median in each column. But in so doing, you've screwed up the rows. Now the medians of the rows are no longer 0. But you can go back and repeat this. You can then subtract, and then you can do this and this and this. And eventually, it's guaranteed that will calm down, and you'll essentially have 0 medians in both directions. And so that's a very popular way, so that everything that's positive indicates kind of more than what in general what's in that row and column, and everything that's negative is generally less than what's in that row and column. But another popular way is to just take each row, every feature, like every gene, let's say, and normalize just the row. So a typical thing to do is subtract the mean and divide by the standard deviation. That's another way. Another thing that some people do is they'll scale the row linearly so that the lowest value is at -1 and the highest value is 1. I don't like that because it gives too much weight to just one sample, whatever is the highest and the lowest. But you can do what you like. Another thing which I think is good is to do no normalization at all. And the reason is that if let's say you do the median polishing, after you've done it, you have some notion of what's greater than what. But I found often I and others looking at the data wonder about what's the absolute expression. Which genes are expressed highly in this big picture, which genes are not. So doing no normalization is sometimes reasonable. Okay, metric. So let's say we're trying to figure out how similar one column is to another column. Well, you have a vector of numbers, the expression for the various genes from column A and from column B, and one thing you can do is just take the correlation coefficient of those two vectors. And in my experience, this almost always gives the best answer. Another thing that sometimes makes sense would be Euclidean distance, which is just a sum of squares of the differences of the numbers in this vector. And one example of when this actually makes sense is, for example, instead of having, let's say, RNA expression in your matrix, if your matrix is something that's naturally between 0 and 1, like methylation fraction, like where each row would be a little region of the genome, and then your question is, it could be completely unmethylated, that's a 0, all the way up to totally methylated, that would be a 1. So even if one sample is perfectly correlated with another, if one of them has a mean of 0.1 and one of them has a mean of 0.9, they're really quite different. So they're perfectly well correlated. They have the same up and down, but one is high and one is low. You may want to say those are not very similar. So in that case, you could use a Euclidean distance instead of a correlation coefficient. Let me just do a little poll here. Does anybody know who knows what I was talking about here and why you might use Euclidean distance as opposed to a correlation coefficient in this case? Nobody? No. Okay.
Do you guys understand what correlation coefficient and Euclidean distance are?
Well, let me ask another question now. Who would like me to go back and explain it so that you get it? Who's interested or who wants me to move on? So who's interested?
I'm interested.
You're interested. Okay, we have 3 interests. Who wants me to move on? Okay, 4 interests. All right, let me try this again. So, correlation coefficient, what is that? That is a measure of the extent to which,
Do you want that?
yeah. Well, no, I'll just, let me think how to do this. Right. So let's say we have 2 vectors of numbers. In our case, the vectors of numbers will be let's say the gene expression values for sample 1 and the gene expression values for sample 2. And the question is, how similar are they? Well, one thing you probably know about is the correlation coefficient. So, and what the correlation coefficient looks for is, do these 2 things go up and down, or in my case, left and right, together? And so these things I just did are very correlated. Now, if they're right on top of each other, they're very correlated, but they could be separated and still be very correlated. So in this example, when I'm talking about methylation fraction, you could imagine having 2 methylation fractions, which change as you move across the genome, and they're very correlated, but one is small values and one is large values. One is always near 0, and the other is always near 1. So you might want to, and in that case, if you did correlation, you'd say, oh, they're very similar. They're all correlated. But you probably, more likely biologically, you'd rather say, no, the methylation in this sample is very low, and the methylation in this sample is very high. And so they're not similar. So I don't want to use correlation coefficient. I want to just measure the difference point by point and maybe square it. The difference squared, the sum of the difference squared, that would be what's known as Euclidean distance, or squared Euclidean distance. And so that might make more sense. Okay. So as I was saying before, we're only talking about an agglomerative hierarchical clustering. And what does that mean? You start off, every sample, say, is a cluster. You call it a cluster with one thing in it. And then you start, you look at all the various pairs that you could put together, and you find the best pair to put together into a new cluster. And then you're going to look again for another pair, maybe this singleton and this pair I made before, they'll go together, and you just keep doing that. That's the process of agglomeration. Let's see. Right. And so there's even if you have in the previous slide, we chose what is the distance, or what is the similarity between one sample and another sample. Now, in order to decide what to agglomerate next, we have to answer the question, what is the similarity between this cluster and that cluster? And so one thing you can do is you can consider all the pairs of samples, one from this cluster and one from another. So you have all these various pairs. You can imagine how many, there are many. And one thing you can say is, well, what's the average distance between them? What is the average distance for all these pairs? And that's what I'm going to call the distance between that cluster and that cluster, or the similarity of that cluster and that cluster. That's called average linkage. Then there's something called complete linkage, which means of all the pairs, I'm going to just take the ones that are farthest away, or single linkage, take the ones that are the closest. And then there's another method called the Ward method. And what that does is it does essentially kind of average linkage, but it has a penalty if if you're putting together a cluster with lots of samples and a cluster with just a few samples. So it's trying to get your splits to be even-ish. Even. And that's what word clustering is about. And I'll show you an example where I think it's good. So this is an example where we had no normalization of, this happens to be RNA expression values. These are samples, these are genes. And we're just using average linkage. And then what we get is this kind of a cascade where you have a little cluster here, and then it adds one, and then it adds another to the next cluster, and then it adds a couple more. But you get a cascade like this instead of a branch and a branch and a branch and a branch. And so in this case, I should show what happens when you use Ward on this. But generally, if you use Ward instead of linkage instead of average linkage, it will kind of break up into groups, which each one of which breaks up and breaks up and breaks up. If that's what if you care about that. So what I usually do is I usually use the top 2,000 genes by standard deviation. I usually use correlation for the metric, except the example I showed. I usually cluster in two ways. One is I median polish and I do average linkage clustering, and the other is I do no normalization and I do the Ward clustering method. And it's called Ward.D is the precise one in R. Okay, so I'll just leave it at that. That is what I normally do. In other words, I normally cluster it two different ways, and I kind of look and say, are these telling the same story? And if not, then I'm somewhat suspicious of the story that one or the other is telling. Hopefully they'll kind of tell the same story. Any questions? Right. So now I'm going to move on to a kind of another topic, which is consensus clustering. And what I've said here is that the consensus clustering is trying to answer the question, what structure in the clustering is stable? And it is, but in a minute. And in fact, it's somewhat reminiscent of what I just said, where I said, oh, let me cluster it two different ways and make sure what I'm seeing is in both ways, then I'll believe it. Consensus clustering is kind of like that. If you do your clustering and you get some things and you say, oh, this is really great, I have a great story to tell. Consensus clustering says, well, perturb your data a little bit and see if it's still there. If it falls apart, it probably wasn't true in the first place. Another reason somebody might try to use consensus clustering is to try to answer the question, how many clusters are there? Yeah, I know we need the hierarchy like I was saying before, but really, at the highest level, how many good, solid, robust clusters are there? So I'll figure that out by doing some clustering, perturbing, seeing how much the clustering changes. So how does it work? Well, what you do is you repeatedly remove 20% of the samples and recluster. And this is a mouthful, but let's step back before we read this. So again, the idea is you have all your samples, but you're repeatedly randomly going to take 20% and set them aside. Now, some of the times, let's say, let's call it sample 1 and sample 2. Some of the times, sample 1 and sample 2, neither of them will be set aside. So then you can ask the question, did they end up in the same cluster? Oh, okay, I forgot to say something. So what you do here is you pick a number of clusters. Remember before we were talking about k-means, where I told it I think there are 3 clusters here. Now, find me 3 clusters and tell me what's in the 3, which samples are in the 3 clusters. So here, you're going to remove your 20%, but then you're going to say, and let's go with 2 clusters. And then so you run k-means or whatever method you want, and you get 2 clusters. Of course, you had set aside 20% of the samples, but of the ones that remained, you have, say, 2 clusters. And you can take a note of sample 1 and sample 2. Were they in the same cluster, or were they in different clusters? And what you want to, so sometimes, I mean, and there's, now you take a different 20% aside, and you do it. Sample 1 and sample 2, if they were not set aside this time, they may be in the same cluster or different clusters. There's no notion that they were in the same cluster as last time because you redid it. You don't know which cluster is which. But you do know that for this clustering, they're either in the same cluster or different clusters. And so you keep track of how often, when they're both, when neither of them was set aside, how often are they in the same or different clusters? Okay. So I'm going to show you what this looks like using a package, an R package that's available that you can download and install. And I'm going to start with some very fake data. So let's think of this as gene expression data. Let's say these are samples, these are genes. Obviously, this is fake data. And obviously, this whole batch of samples is really very similar to each other, and should be one cluster. This is another cluster, another cluster. So there's kind of 4 natural clusters here, 14 there, just none there or 1 there. Okay, so that's the input data. That's the data from which we're going to randomly remove 20% of the samples, cluster it for 2 clusters, and cluster it for 3, for 4, and so forth. And here's what we get. This matrix is representing that count I was talking about. What fraction of the time, when sample 1 and sample 2 are not both discarded, what fraction of the time are they in the same cluster? And if that fraction is near, if that fraction is near 1, if they're almost always in the same cluster, we make it blue. If it's near 0, we make it white. And so what happens here, okay, yeah. So what we've done here, I'm going to go back. So we're going to start using this data here. This is the one we're going to use at first. So we throw it into this consensus clustering, and it finds oh yeah. So when I say to it, find 2 clusters, it does so, and it very reliably actually puts all these things in one cluster, and these guys are all clustering with each other, and these samples are all clustering with each other. When I tell it to find 3 clusters, you kind of generally get 3 clusters, but you get a lot. There are pairs here where they're neither in it together always or out together always. Sometimes they're in it together, sometimes they're out. They're not in it together, and that's why you get this middling color. When I ask it for 4, I get a good solid 4. So it's either white or purple. When I go on and I ask it for 5, you can see there's some confusion here, but it's still sticking with 4. It doesn't give me it won't give me the 5 I asked for because there's just no 5 in the data. And same here, when I ask it for 6, it's messy, but if anything, it looks like 4, and when I ask it for 7, it looks like 4. So this is telling you quite clearly the answer is either 2 or 4, and 4 is even cleaner than 2. Okay, yeah. So there are supposed methods for, like, running it and getting a number, and from that number it's going to tell you how many clusters there are. But I've never been able to get any of these methods to be reliable. So to me, this is something we just do by eye. And you look at your data, and if there's something really clean, like this, you say, oh, that's it. That's a clean, stable result. And you might say, this is a clean, stable result if you want to say there's 2. But 3 is not a reasonable thing to say, nor is 5, 6, or 7. We seem to have lost the top.
Oh well, it's 2:35.
No, I'm looking, well, let's see. I think what I've done is I've gone on to the one where there were 14 clusters.
Right.
Yeah, right. So you can see that you get these middling colors showing that it's not quite clear until you get to, well, oh right. This looks kind of good at 10, but here's 14 is good, but then when you go up to 15 and 16 again, you get 14, if you were to count them out, you'd see. And then here is when I pass it just 1. Then you see none of these are clean. I passed it the one that just had 1 cluster. So that's how you use consensus clustering. Now, I should have updated the slides. I forgot to. There's one other thing that I think is important to say about clustering nowadays. So nowadays, there are technologies like 10x. How many people have heard about 10x? Nobody? Oh, okay. Well, the notion of 10x, to the extent that I understand it, is that you can take, let's say, a bunch of blood, so you have many, many cells of different types, and throw it into your 10x machine, thousands, let's say, 2,000-3,000 cells, and you get a gene expression profile for every one of these. So you may have 3,000 samples. It is very hard to make the kind of clustering. Let's go back. This, yeah. This is, I don't know. This is less than 100. So you can imagine what an unreadable mess it is if you have, 2,000 or 3,000 cells. So instead, what is popular in that case, instead of doing this, is to use some technology to take all your samples and kind of try to throw them into a two-dimensional picture and see, so that the ones that are kind of the samples that have a similar gene expression profile will be near each other on the plane. And a popular way to do that is called TSNE, T-S-N-E, T-SNE. So I just thought I'll throw that out. That is another thing that is now quite often done when you have thousands of samples, is you use TSNE to kind of just lay them out in 2 dimensions. I should have a picture of this. I'm sorry, I don't. I apologize. And then you kind of say, by eye, you say, oh, here's one cluster, there's another cluster, and so forth. Okay, now I'm just going to briefly talk about some packages that, as Vishal said, that I wrote. I wrote them a while ago, before there were nice packages. Okay. So there's actually, so have you used R packages yet?
Not these particular ones, but they've been doing, up until now we've covered till R graphics.
Okay, so but you know the general idea that you have your
Can't
R,
load packages.
and you can download and install a package, and then it gives you extra function, new functionality. So yeah, so one package is called BSW-10, and Vishal will supply you with the actual software so that you can install it. But it produces these kind of plots. There's another package called BSW-heat. And the reason I made this package was because I actually made this figure. And I had to make this figure, and it was very, very painful. And I knew that once I did it once, people would ask for it again. So I made a package to make it much easier to make than it was the first time. And some of the features of this are, we kind of wanted this, they wanted things split up by groups, but within the groups they wanted to split up into kind of smaller subgroups. So I had a big gap here and then lesser gaps, or same thing here. We had big gaps, lesser gaps, big gap, and so forth. So there was all sorts of crazy stuff going on in making this heat map, as it were. Oh, another aspect of this heat map is that some of this was just kind of displaying continuous variables, and some of it was just displaying things that could be either, say, mutated wild type or insufficient read. So just three different values. So like here, there's just 3 different colors, but here you want a whole continuum of colors, and so it was a complicated, situation. And I wanted to make a package so that if that came up again, I could just do it quickly. And similarly, another type of thing that I had to do was a heat map like this, and I also wanted the package to be able to do that. Before we get into it, some caveats. These 2 packages should be combined into one. It's something I might do in the future. So for now, one has to live with 2 separate packages. They should be put in CRAN. That's also a project for the future. And there's a very popular alternative called pHeatmap that a lot of people use. So you might want to check that out as well. Okay. Well, I'm just going to tell you that it has one of the ways that you can use this is like if you have this plot and there's all these some feature like this, and you say, I wonder what this is. You can make a tall version, and so it's the same thing, but now big enough so that you can write the names of the genes. Of course, when you make it that big, it's huge. It's very tall. And I'm gonna say something that's just a little bit of a kind of a detail, but I'll say it because it could bite you if you try to use this package and don't know about it. Is that Adobe Reader, right, a popular piece of software for displaying PDFs, has a bug. I don't know if it still does, but for many years it did. And the bug was that if the size of the objects you were drawing in a PDF was too big, it would just give you a white piece of paper, and it wouldn't draw any of the objects. So to get around that, there's a global scaling factor that you can pass into the functions that do this plotting, saying, oh, make it a quarter the size. Make everything a quarter the size. So you would set GX to 0.25, and then it would be smaller. And then for some reason, Adobe Reader would be happy, and it would display it. Okay. Another thing is you can type these things and have it show up not in a PDF, but just on your screen. But when it shows up on your screen, it may be too big. It may not fit. So you can also use this GX to shrink it down so that you can see it on your screen when you're still debugging and so forth, before you're going to write it off to a PDF, which is what you're probably going to do eventually. So this is some actual output of BSW-heat, where it actually goes very far to the right, but it was this. I don't know how many of you know about what's known as the TCGA, the Cancer Genome Atlas. So what that is they've done gene expression and profiling and mutation profiling and all sorts of profiling for literally thousands of breast cancer samples, but hundreds of all sorts of other types of cancer. And that data is available, and you can download it, and they give you data as to what subtype each one of these samples was clinically. Here are the different subtypes: estrogen receptor positive, progesterone receptor positive, HER2 negative, so forth and so on. And when I had just written BSW-heat, I took this thing and I threw it in there, and I said, this will surely break. And it didn't. It actually came right out, gave me this plot that went out forever, and it was an unusual day. Okay. So learning to use the packages. In addition to the package, Vishal will supply you with two programs, two R scripts, one called BSW-clust examples.r and the other BSW-heat examples.r. And the best way to get started is to step through these examples. So you can take a little chunk of the, usually at the top they make some data to play with, and then it displays it in various ways. And you can easily see what changed between example 3 and example 4, and look and see how the output changed. And I would also, encourage you to read the comments in the code, because that's meant to explain what that example is trying to show. So that's really the best way to get started. And for what it's worth, I think also Vishal will be giving you something called terminology.pdf, which you can blow up later, but it shows the terms, like in the output, here, this part is called the heat map, and this part is called the heat map ramp, and so forth. That will help you using the package to know what things are generally called. Okay. Now, something to mention about BSW-clust 10. So I don't know, how much R you guys have done, but typically in R, the way you're supposed to do graphics is you have a bunch of calls which produce graphics. And if you want to make a PDF file, you just start by saying, okay, from now on, all my graphics are going to this PDF file. And you do graphic, and then you say, okay, I'm done, close the PDF file. And now you have your PDF with the graphics. That's the normal R way to do things. And it's a nice way, I like it. BSW-clust, on the other hand, doesn't do that. Okay. Oh, yeah, actually, you know what? I'm talking about this. Let me step back and say that the first thing I want to say is that creating a plot is a two-step process. First, you cluster. You decide what the clustering structure is going to be, what the dendrograms are, and so forth. So, step 1, you cluster. Step 2, you plot. And why is that? The reason is that clustering can take a long time. So when you call this cluster function, you go get a cup of coffee, chat a little with some people, and then it may come back and it may be done. And then, when you plot it, almost surely you won't be happy with the plot. There will be something you want to change. So it would be terrible if you had to cluster again each time. So the idea is, now you're just going to mess around with the plotting until you're happy with the way it looks. And you don't have to recluster because those are separate processes. So that's why it's a two-step process. And then I was talking about why does this plot to file exist. So you could do it in the way R normally does things. Say, I'm starting a PDF file, it's of this size. Now I'm going to call BSW plot, and therefore it'll plot to the PDF, and then I'll say dev.off, which means I've ended the PDF file, and that you could do that. But that will be very painful. And one reason it'll be painful is well, it has to do with resizing things and so forth. So in general, in R, if you plot like a bunch of stuff, and then you make the window, and let's say you just do it to a window in your computer. So you have a plot. I hope you've all done this by now, right? You plot. Okay, so here's your plot. Then if you make the window narrower, everything gets narrower, except the text. So if it was designed to look good at this width, then you do this to make it fit. All of a sudden the text is all over yourself and it looks pretty crappy. The text doesn't shrink in general. So also, if you wanted, let's say, if you're doing a heat map and you want your things to be actual square, which actually is very visually pleasing, it's very hard to figure out exactly how high and wide this thing's going to be so that squares are squares. So it's a real pain in the neck. So BSW Plus operates in a somewhat unusual way in that that there's a kind of everything starts being plotted so that text is about 0.2 inches high. Like text, that's how big the text is, and then like every row is like the size of a row by default will be so that there's enough room for the text to go in, and the size of a column by default will be that same size so that the text will. So you make this, you make the heat map, and then it starts plotting stuff on the side and around, and it plots out everything you've asked it to plot. And then it stops and it says, okay, so we've plotted all this stuff, how big is it? It keeps track and it knows how big it is and says, okay, so now I'll make a PDF of that size, and I'll put this in just the right way so it'll fit nicely with a nice little margin, and it's much easier. So that's why it operates in this strange way. Now, this is somewhat painful. Most of the arguments of BSW Plus plot to file are found in the help pages for this. So, you know about help pages for R functions, yes? So there is a help page for BSW Plus plot to file, but it doesn't have much in it. One of the things it has in it, it says, you know, here's argument 1, argument 2, argument 3, and as you may have noticed often in R, they'll say ... These are extra arguments that are passed on to some other. So what happens, of course, not surprisingly, is BSW plot to file uses BSW plot. And so if you want to give arguments to BSW plot when you're using this, that's what the ... So you're going to just add them in there. But they're not documented for this function, they're documented for that function. So you have to kind of look at both the help pages for both of these to find all the things that you can mess around with. Or you can ask me or Rashad. Okay, getting to the end of this. BSW heat. This has a similar file like the one plot to file. This is just plotting to PDF. But this one is going to turn around and call this one or that one. And what this one does is it plots a matrix, like you give it a matrix of numbers, it will make those continuous color scales and plot that. But you may recall that I had that, the thing that motivated this package was that rather complicated figure where some of them were continuous values and some of them were just 3 colors and so forth. So you can also pass it, you can figure out the colors yourself and just pass it a matrix of colors. So this function will call this function, which by the way will make a bunch of colors and call that function. Or this function might call that function directly, depending on what arguments you give it. And this has the side effect that most of the arguments that might control how a numeric matrix is shown are documented for this one. You can pass them to this guy, and he's going to turn around and pass them to there. Same. So you need to read the documentation for all 3 if you want to look for some particular thing. So, okay, enough caveats. And so this we're going to skip because at some other point Vishal will
We'll do the practical
do the practical.
tomorrow at conference room A. And one of the things, overview of statistics by Dr. Ben Wittner.
Okay, so the overview is a word about frequentist versus Bayesian. We're going to talk about what distributions mean, sample mean and mean, standard deviation and variance, then hypothesis testing, power and sample size. Anyway, I guess here's what we're going to talk about. So, frequentist versus Bayesian. There are two major ways of doing interpreting statistical analysis, frequentist and Bayesian. Most biological analysis is frequentist. So we're not going to discuss Bayesian. Everything I discuss is from a frequentist point of view. Just in case you're familiar with those terms. Okay. So distributions. So imagine you have a procedure that produces an output data. Examples, you can measure body temperature. Another example would be to ask a person to react to a statement with, strongly agree, somewhat agree, neither agree, these 5 levels. Or you could do some procedure to determine blood type. This is an example. Now these are actually 3 different types of data. This one is a continuous valued thing, or in any event, what's really different about it is that the size of the output has meaning. Each degree hotter has a real physical, biological meaning. And in this case, there's an order to these things, but there's no obvious notion that this difference is twice as much as this difference or anything like that. So this is a kind of another type. And then this is a third type where not only is there any meaning there's no size to these things, but there's no order either. So all these different types exist. Okay. So a set of the relative frequencies of the various possible outputs is called a distribution. And here's an example blood type. In North America, I think we have these relative frequencies of the 4 different blood types. So that's a distribution for blood type. Similarly for temperature, we could break it down into half a degrees and have the relative frequencies, and that's the distribution of this procedure. Okay, now getting on to sample means and means. So we're using this example of taking temperature. Imagine we took temperatures 4 times from different people. So statisticians would call the collection of 4 outputs a sample. Now this is a little confusing because biologists and I in the previous talk use the word sample to mean a single piece of tissue or data or a single study subject to be characterized. For this talk, I'm going to try to be rigorous and say each one of these is a specimen, and all 4 is a sample. Okay, so the sample mean is defined as the average of the 4 numbers gotten by repeating the procedure 4 times. So we just take the values for these 4 people, we add them up, divide by 4. That's the sample mean for this sample. Now the thing about sample means is they change. If you repeat the procedure again and take 4 different people, you'll get a different mean. So here I'm kind of simulating that process. We have temperature, and like person 1, this was, I randomly chose this temperature, 2, that temperature, 3, that temperature. The red line is showing the sample mean for these two. It's like halfway between here, and then for these 3, and then for these 4, and then for these 5. That's what the red line is showing. So it's showing the sample mean as you get a bigger and bigger sample. And if we go way out, you see that when you have small samples, there's a lot of variability to the sample mean. But as you have bigger and bigger samples, the sample mean becomes steadier and steadier until you go way out, and now you see the sample mean is really quite rock solid there. And so the sample mean for these increasingly large samples it approaches a value, and that's the mean. And we usually do not know what the mean is. Right? I mean, if I ask you what is the mean temperature of the citizens of the United States, you don't know. Nobody ever measures everything. So all we have typically is sample means, but we imagine there's a mean out there that we could approach by having bigger and bigger samples. Okay, some caveats. The procedure shouldn't have systematic drift. So if you have a reagent that's slowly losing potency over time, it's not going to approach a mean. And many statistical methods assume that the repetitions that we've done to produce a sample, the repetitions are independent of each other. What happens with one does not affect what's going to happen with the other. So for example, if you're still tuning your procedure, that's not, so that what you do the next time depends on what you saw, that's not a good mathematical sample. A good mathematical sample is one where I've defined my procedure, and now I just do it 4 times or 10 times. All right, moving on to standard deviation and variance. Any questions, by the way? All right, so we often denote the values obtained for different specimens as x1, x2, and so forth. And the sample mean is often denoted by x bar, x with a hat. The mean is often denoted by mu. And the variance is saying, okay, how far off is each specimen's number from the mean squared, and you take the average of that. And this, for larger and larger n, this value, which we do not know because we don't know mu, but this can be approximated better and better by using the sample mean in here in this formula. So this would be called a sample variance. The actual variance, so same deal, as n gets bigger and bigger, this approaches some number. That number that it approaches is called the variance, and denoted by sigma squared. The standard deviation is just the square root of this variance, so it's denoted by sigma. Okay, and this is again that data. Remember, we were looking at the sample mean, and that was the red thing, and it settled down. And we could also compute this sample variance and go up and down by that. So this is up and down one sample variance, and you see it 2 settles down as we get bigger and bigger samples. All right. Hypothesis testing. Okay. So I'm tempted to just read what I wrote, but yeah. Okay. So in hypothesis testing, we specify a hypothesis of no difference, called the null hypothesis, and then we see whether the observed data is very unlikely in the case of if the null hypothesis were true. And if the observed data is very unlikely, when the null hypothesis is true, we say probably the null hypothesis is not true. that last step is a little tricky, but that's the general idea. The null hypothesis is often denoted by H0. And here's an example, a drug to lower temperature. H0, the null hypothesis, is that the mean of the temperatures of patients taking a placebo is the same as the mean of the temperatures of the patients taking a drug. No difference. Blood type, you might say the distribution of blood types among Europeans. A null hypothesis might be that there's no difference in the blood types of Europeans versus, say, Africans. Okay. So that's hypothesis testing. And how do you do it? Well, typically you'll do some kind of an experiment, and that will produce some data like specimen 1, whatever its output value is, specimen 2, and so forth. Plus the notion that, let's say, specimen 1, 2, and 3 are controls, and all the rest were treated. So you have that information. That's something that you produce. And then, based on the test that you've chosen, what will often be done is that this data will go into some function that will compute a number from all this data, a number. And this number is called a statistic. So people tend to think of like these numbers as these are the statistics. But no, they're not. You have to munge it a little bit and you get a statistic. So an example would be, let's say you just took the mean of the temperatures for the controls and subtracted, or let's do it the other way. Well, let's take the mean for the temperatures of the treated patients minus the mean of the temperatures of the controls. So that would be a function. You would take the difference of those two means, and that would produce a statistic. You look puzzled. Gentleman from Korea. You look puzzled. You're not puzzled. Okay, good. All right. So this is like the first step in doing a hypothesis test. There's your real actual data. But what you're going to do now is you're going to say, well, what if the null hypothesis is true? If the null hypothesis is true, in other words, there's no difference between control and treat, if I were to make the same data under that assumption and then run the same statistic function, I'll get some number. Now, of course, this number is not going to be 0, just because there's no systematic difference between controls and treateds. You're still not going to get 0 as a difference of the mean every time. There's going to be variability, so these statistics will actually form some kind of there'll be a distribution of these statistics that you get as you do this over and over again with the null hypothesis in effect. And these numbers, the relative frequency of these numbers, is called the null distribution. It's just the distribution of the statistics that were generated if you actually had the null hypothesis in effect. And then, what we do is we take the actual statistic, which came from your data, and we compare it to the null distribution. And we say, the p-value is what portion of the null distribution is as or more extreme than the observed statistic. Okay. Now, this is a lot of work to do all this. The good news is that the software does all the stuff in blue for you. So all you have to do is do your experiment, generate this data, throw it in, tell it what test you want, and it does all this stuff, gives you your p-value. The bad news is choosing which test to do in which cases is very complex. And that's one of the reasons people like Bayesian analyses, you don't end up with all these different crazy tests, typically in Bayesian analysis. But anyway, that's the bad news. Is that, there's all sorts of different tests, and which test to do when is a very complicated subject that we're not going to get into. here. Okay, so if your p-value is less than 0.05, it's usually considered significant evidence that the null hypothesis is not true. But just knowing that two things are not equal is not the whole story. It's often important to know by how much they're unequal. So this is called the effect size, by how much they're unequal. So an example, you may have a drug that lowers temperature. It actually does lower temperature, but it lowers in such a little amount that it's of no use. So statistical significance is only part of the story. Effect size is the other word. Okay, right. So moving on to power and sample size. So when you're planning an experiment, we often wonder how many specimens of each type we need in order to have a reasonable chance of getting a significant p-value. And when you're writing for a grant, you often have to answer this question. I need this many mice, control mice, I'm going to need this many treated mice, and that's why you have to give me this much money. But you have to show that you have reason to believe that you have some chance of having a positive result. So you need to do what's called a sample size calculation or a power calculation. So the chance of getting a significant p-value is called the power of the experiment, and the number of specimens is called the sample size. Okay, so the power depends on the experiment's design. For example, which statistical test will be used. But it also depends on the sample size. I mean, that's an easy. That is one way to get a significant result. Just have a huge N. But as we said before, just having a huge N, if you have a very small effect size, is not really great. But anyway. But what does the power depend on? The experiment's design, the sample size, the effect size, right? The bigger the effect, the fewer you need to have. The fewer you need before you have a chance of getting a significant result, and often the variability. The more variability you have in the data, the harder it is to see a difference between two groups, to get a p-value that is less than 0.05. Okay. So, if you're, let's say, applying for a grant and you want to do a power calculation, you're going to have to say, you're going to need to hypothesize, say that I think the effect size is this, and I think the variability is that, and then therefore, with this experiment's design and this sample size, I'll have a 80% chance of getting a significant result. Often, in order to do that, you need to have some reason to say that you think the effect size is X and the variability is Y, and often you get that from pilot data. I have no idea why this is here. There are online power and sample size calculators. So here's one, I guess. I haven't tested it this year, but it was there last year. Or you could just search, Google search, obviously. Okay. Now, multiple hypothesis testing. So far, we've been talking about a single hypothesis test. But in genomics, you might be doing thousands or tens of thousands of hypothesis tests. For example, you might do one for each gene in the genome, so then you'd be doing 22,000 hypothesis tests. Okay. So, this is I'm going to throw this question out to you. See if you can answer it. So imagine that we're comparing control with treatment for the expression of 10,000 genes, roughly half the genome. So we're going to do 10,000 hypothesis tests. If the null hypothesis is true, in other words, if there's no difference in gene expression between the control and treatment, roughly how many of our hypothesis tests will yield a p-value less than 0.05. Just to get your team spirit up, I've asked this question of Vishal's classes before, and people knew the answer.
Yes.
Should be about like 500-ish.
Exactly. Great. Yeah. So starting with a completely reasonable number of genes, if you just do these hypothesis tests, roughly 500 of them will come back with p less than 0.05.
By the way, that's 0.05 times 10,000, in case you got something.
Yeah. I'm not going to, I was going to explain why, but I'm not going to go into that. So I'm just going to, oh yeah,
There it is.
That's just the answer. Okay. And just to illustrate this, what I've done here is I've taken some controls, actually 5 controls, 5 treatments. I've just put in random data. I've done a t-test for each one of these 10,000. And I said which ones have p-value less than 0.05. It turns out there were 497. And I plot just those 497. And you can even see it with your eyes. Oh boy, there's a real difference between these and these. It's beautiful. But let's remember that this is just the monkey typing at the typewriter. Right? I mean, have you all heard the notion that if a monkey sits and types long enough, he'll eventually type out all the works of Shakespeare? That's true. And that's what's kind of going on here. Now, slightly different, but basically that's the idea. In our world, if the monkey sits and types, some Shakespeare comes out. And I still get people saying, yeah, but for this particular gene, it is significantly different. And I have to say, okay, if you want to work up that gene, be my guest. But there's no difference. There's no evidence that, how do I say it? I tend to say, there's nothing to distinguish your output from the output where the null hypothesis was true. And sometimes we go round and round. But I think this kind of makes the point that you have to be careful about this kind of stuff. So how do we correct for multiple hypothesis testing? Well, one way is the well-known method of Bonferroni. You take the p-value, you multiply by the number of hypothesis tests, and that's your new adjusted p-value. And what it's a little hard to state what Bonferroni is doing. It's maybe I'm going to give it a try though. Okay, this is a little wrong, but I'm just going to say it. What Bonferroni is trying to do is say, like, if I cut a Bonferroni off at 0.05, whatever my hits are, I want there to be like a 0.05 level of confidence that every single one of those hits is true. None of them are just by chance. None of them are by chance. To 0.05 level. So that's what that's called controlling the family-wise error. Controlling the error for all of them. Family-wise error rate, FWER. You may see that. Does that make sense? Okay, so this is a popular thing to do. Let's say you're proposing a study, and in that study you're going to do 3 hypothesis tests. Maybe one is your main aim, and the 2 are kind of sub-aims or something like that. Then it's quite common to say, and I'll do a Bonferroni correction. So you'll take your p-values, you're going to multiply them by 3, and those will be the ones that you claim in your paper. So that makes sense, because if you're only making 3 claims, you'd like them all to be every single one of them to be believable. But if you apply this method to genomic data, where you have 10,000 or 20,000 or more hypothesis tests, you typically get nothing. You get no hits. So people said, oh, that's no fun. Let's look instead at this thing called false discovery rate, FDR. And what that is that it's kind of an estimate of the number of false hits divided by the number of hits. So let's say, like before, we had roughly 500 hits. If we believe, yeah, maybe 50 of them are just by chance, but the rest are probably true hits, then you'd say you've estimated your FDR to be 10%, 0.1. So we tend to use this in genomics instead of this. And what this is that it's an estimate of the portion of your hits that are false. And it can be estimated empirically, like these programs do, or using a method called Benjamini-Hochberg. For this, you just take all your p-values, your individual p-values, and you throw it into the function, and it gives you back what are called Q-values or FDR estimates, and then you can cut that at some threshold. Common thresholds to use are 5%, 10%, or 25% for FDR. And what I think I did here is I took the 10,000 p-values that I generated from the null hypothesis, and I fed them into Benjamini-Hochberg, and I got these 10,000 Q-values. None of them were less than 0.05 or 0.1. One was less than 0.25. So essentially, it was smart enough not to be tricked. Right? And we had the null hypothesis was in fact true here, and BH wasn't tricked. And by the way, when you have one, to say that, oh, among these, 25% may be fake, but 75% of the one that's crazy. Right? So for you to really feel like, oh, I got something, you need to have some number of hits for BH to make sense. So in terms of software to use, right. So if you Google statistical power calculator genomics, you get a lot of things for GWAS. So for planning your GWAS study. Everybody know what a GWAS study is? So you get a lot of things for that. It was much harder to find things that would try to do sample size and power analyses for gene expression comparisons or the kind of stuff we've talked about today. Here are a few that I found seem pretty good. Again, this was a year ago that I last checked them, and so I can't guarantee they're still there. And that's it. Any questions?
Well, if there are no questions, then